All right, we are live. Hello, everyone. We are now part of the third Tech Talk for the Unikraft Summer of Code. And today our guest is Gaulthier. Gaulthier is a PhD student at the University of Liège, and he's been involved for the past years with the Unikraft project. He's been working extensively on the muscle port and on what we call static and dynamic analysis. This is mostly due to syscalls, things that are now going to be integrated in Craft. And he's also working on a very interesting topic that's going to be the main talking point of his today, which is memory deduplication. Without further ado, I'm going to leave the floor to Gaulthier, and he's going to talk to you about this kind of very interesting subject. Gaulthier, you have the floor.
Yeah, okay. Thanks a lot, Razvan, for this introduction. So yes, hello everyone, I'm Gaulthier Gain, PhD student at the University in Liège in Belgium. And today I'm going to talk about memory deduplication with Unikraft. So yes, for this talk I will not go into too much detail, so I will just give you an overview of my work and my research. And yes, for some of you, there will be some obvious concept in the first slide, but it's just to get the right background for the rest of the presentation. So sorry for that. So let's start. Okay, so as I said, a bit of context first. So in our research, so we mainly work with executable files, and these ones are produced by the compilation process, which translates human readable source code into machine code, and this code is then executed by a processor. And on this slide, yes, we can see the basic pipeline, which is divided into several steps. So yeah, I won't explain all these steps here because it will take too much time, but the main information to take into account on that diagram is that after all these steps, so we get an executable file, which is also called an L file in Linux. Okay. And now with this compilation pipeline in mind, so let's come back to UNIKERNEL and more especially to Unikraft. So a UNIKERNEL is just an L file which can be run as a virtual machine on an hypervisor. So for example, we have the KVM hypervisor that normally you have that you play a bit with it. And more especially, so an executable file can be divided into two different views. So the first one is the section view, and after that we have the segment view. So in the first one, so each section contains the necessary information for the linker. So for example, there is a text section which contains the code, there is a data section which contains the data, there is a raw data section which contains the read-only data, and so on. After that we have the second view. So the second view will rely on segments, and this segment contains the necessary information for the program execution. So once the program is run, so the underlying operating system will load all these segments into virtual memory. And something that it is important here, that is also important, is that there are also some parts of the L file that are not loaded into memory. So for example, this is the case with the debug or the node sections. Or in opposite, so a new section or segment can be added by the underlying operating system during the program execution. So it is the case with the stack or the heap, which will be updated dynamically. Okay. And now with this ELF representation in mind, so we will analyze the memory deduplication between several UNIKERNEL instances that run on the same hypervisor. So first, what is memory deduplication? So basically, it is simple. So memory deduplication is just a kernel feature that allows to share memory pages with identical content between multiple processes or virtual machines. And in that case, so in that diagram, so all pages which have the same color will be mapped to the same frame. So instead of having 4 green pages that will be mapped to 4 physical frames, so we get only one frame that is mapped to these 4 green pages. And so yes, so this approach allows to save memory by mapping several guest pages with identical content to a same host page. The question now is, how does memory deduplication work? So it is quite simple too. So basically a daemon process performs some periodic memory scan of each virtual machine, and then it will merge identical pages that will be mapped to a same single frame. And in order to establish this comparison, so the underlying daemon will perform some hashing of guest memory pages, and then it will compare the different hashes in order to find a matching one. And in case, so if it found a match, it will then execute a per bit comparison in order to avoid the false duplicate, since two different sequences may give the same hash. And we will see that having a good sharing will considerably decrease the amount of memory needed by the underlying system, and thus also, so it will considerably increase the overall performance on the same underlying system. Now we will consider that we have several unikernel instances with different microlib configurations. So normally you have already seen what is a microlib. So this means that when we have a different configuration, so this means that some microlibs can either be inserted or removed between the different instances. And in that case, so we can clearly see in the second instance that this one contains one more microlibs than the first one, and in that case we can clearly see that it is a UK string. So it is in the red boxes here. Yes, and since we have a new microlibs which modifies the microlib order, so the resulting unikernels will also have different memory representation, and we will see that it will have an impact. But concerning the microlib order, so this one is fixed by the underlying build system. So it is the Unikraft build system. So the Unikraft build system does not have a global overview of all the microlib that I use by the different instances. And why? Because each unikernel is built in an individual way. So for example, we built hello world unikernel, and after we can build another one, and this one can have different microlib representation. And yes, so we will see that having this different microlibs configuration between the different instances has a considerable impact on the memory sharing. Okay, so now if we consider the memory representation, so we can see that the text section, which contains the instruction, is divided into several pages, and this one in this diagram are represented by red boxes. Okay, and here we can see that each microlib can either be contained within the same page or be divided into several pages. So for instance, in the first unikernel, we can see that UK timeconf is contained within a page, and basically in the second instance, it is contained within 2 pages. And also, yes, so in this scenario, we can see that having a new microlib on the second instance will introduce a first issue. So indeed, as the build system does not have a global overview of all the microlibs that I use by the different instances, so the new microlibs, in that case, yes, UK front, will be placed between 2 other ones, but only on the second instance. And in fact, we'll see that this insertion will shift all the microlib code across different pages, and thus it will decrease the memory sharings, since some pages will no longer be identical. So yes, just let's consider a brief example. So in the first instance, so the second page will start with the UK bus code, so it is in the yellow box. While on the second instance, so the second page, will start with the UK front code. And after that, all the next pages in the second instance will be impacted by this change. another issue that we can have is that concerns binary instructions. So if we take the previous configuration and if we do a kind of zoom on the UK bus microlib code, so we realize that some instructions are different. And for example, this will be the case with the move and LE instructions. So normally you have seen that these instructions use some specific addresses from other sections. So for example, of the data section, of the raw data section, and so on. And thus, since all these sections do not start at the same location between all the unikernel instances, so the addresses that I use by this instruction are also different. So, and actually, so in this example, even if there are only just a few bytes that are different between these two pages, so we can clearly see in these two boxes that we have different bytes between the two instances, and basically it will be enough to lose the page sharing between these two instances. And we will have exactly the same issue with the call instructions, since addresses that I use by this instruction may also be different between several unikernel instances. And the problem of this issue is that it will considerably impact the memory sharing. And to circumvent these two issues, so we design an algorithm that has a global overview of all the microlibs that are used by the different unikernel instances. And how this algorithm is working, so it is simple. So first, it will reorder all the microlibs that are not common to all instances by placing them at specific position. And thanks to that, so it will avoid the previous issue that we had before with the call instructions. But actually, yes, for this part, it may be a bit not trivial if there are more than two instances, so I will explain just after in the next slide. And yes, so this algorithm, in addition, will also align each section of the different instances at the same location. And in that case, so we can see that the data section of the first instance is aligned with the data section of the second instance, and thus we get exactly the same addresses for the move and EDA instruction between these two instances. So if I just quickly show the previous slide, so the data section here is placed at this address, and after that, by using our algorithm, we have exactly the same address for the first instance, which is equals to the second, which is equals to the address of the second instance. And basically, yes, thanks to this approach, so the memory sharing is considerably increased. As I said before, so when there are more than two unikernel instances which use different sets of microlibs, it is a bit more complex. And indeed, so if some microlibs are only common to a subset of instances, so it is necessary to align them to specific addresses. And by using these specific addresses, it will create some gaps in the memory virtual space. So, for example, in that case, yes, it will be necessary to align the UK ring microlib by leaving a gap on the second instance in order to have exactly the same addresses in the binary instruction on all other instances. And it will be exactly the same on the first instance with the UK libd microlibs. Also, yes, and this gap will not add any padding on the L5. It will just add some memory padding in the virtual space of the unikernel. So basically, yes, so we cannot just place a microlibs at the end and say that it will work. So we need something a bit smarter if we have several instances. Yes, concerning our work, so we are working on three different components. So the first one is a binary analyzer framework, which is developed with Unikraft in mind. And its main objective is to analyze and parse ELF and object files in order to gather some specific information, such as, for example, the list of sections, the different functions, the different instructions, and so on. This tool can also establish a complete memory view or map of the different microlips which are present within the resulting binary file. And finally, this one allows also to gather some stats on page sharing by computing, for example, the number of pages that can be shared, the difference between all the different pages, and so on. And actually, yes, we use this tool as a simulation for our early work on the memory deduplication. And since we saw that the sharing was quite good with this simulation, so we developed another tool. After that, we have the aligner tool. So this tool directly works on UNIKERNELS binary and will allow to perform a new linking operation by aligning microlips and section according to a specific memory mapping that was established by our previous tool. And finally, so we also did some updates and improvements on the KSM daemons. So the memory deduplication daemons that allows to share to merge same pages, and what we did we did some improvement that allowed live analysis to see the memory behavior during UNIKERNELS at runtime. We did also several experiments with memory deduplication, so due to time constraints, we will only give you a small overview of some of them. And we'll first present some results by considering two unikernel instances, so a simple hello world unikernel that does an infinite loop, and after that SQLite unikernel which does some classic database operations. And using our binary analysis tool, so we first analyze and compare the binary representation according to whether they are aligned or not. And then we run these two instances on an hypervisor, and we collected performance and memory sharing result using the KSM daemon. So yes, so here we represent the ELF sections and the respective start addresses of the two previous instances, so Hello World and SQLite. So the first table illustrates a section with unaligned unikernels, and table 2 the ones with aligned unikernels. What it is important to highlight here is that without any alignment, all sections, so except the first one, so the text section of unaligned unikernels start at different addresses. And this means that all pages within this section will be different since they use different addresses. So for instance, the raw data, the data, and the BSS section do not start at the same addresses in the first table. And in opposite, when we use align unikernel, we can see that all this section will have exactly the same addresses and will be placed at the same location. After that, we did an analysis on the microlips location within the binary file. And what we can say is that for unaligned unikernels, it results that most of the microlips are located at different addresses, so except the first one. And actually, why? Because it depends on the linker script. And in that case, all microlips code after the main application code will have different start addresses between the two instances. And like for the section, so it means that all pages which contain the code of this microlips will be different in memory, since they have also different addresses. And now, if we consider aligned unikernels, so we can observe in these two tables that the same microlips in both instances start exactly at the same addresses. And we will see just in the next slide that is a very good impact on the memory sharing. So now let's compare the memory sharing between unaligned and aligned unikernels. And in this table, so we can do two important observations. So the first one concerns the memory sharing, and the second one concerns the inflation. And by inflation, so we mean that aligned unikernels will consume more pages since they are aligned on the page boundary and are just a bit bigger than the unaligned version. So it is why we have a bigger number of pages in the second column. So when we deal with aligned unikernels. And yes, so we get a bigger text section and data section, but it goes also on and on with the memory sharing. So we clearly see that for the aligned versions, we have better sharing, since we can obtain more or less 48% of memory sharing, and instead of more or less 1% of memory sharing for the unaligned instances. And in that case, so it's quite difficult to get better sharing, so to be higher than 48%, since the SQLite main code has a text section of a specific file, so the number here, because it means that yes, at least 210 pages cannot be shared with the hello world unikernel. So we cannot get better sharing because of the core code of the application, which is not shareable at all between these two instances. Okay. So we also perform some live analysis by relying on the KSM daemon. And in these two different graphs, so we can see the memory sharing over the time. So the blue line represents the number of pages that are shared between these two instances, and the orange line is the number of unshared pages. And as we can see on these two plots, so there is a big difference between aligned and unaligned unikernels. So the memory sharing is considerably better when we deal with aligned versions, since the KSM daemon will merge a bigger number of pages. And in addition to the sharing, so we can also see another observation. So we also observe that the KSM daemon has some overhead. So indeed, we can clearly see on these two plots that it takes several seconds in order to converge. And we guess that due to this convergence, it will also consume some CPU cycles. So we also did some performance testing by relying on the KVM performance tool. So first we analyze the completion time of SQLite with aligned and unaligned versions, and then by enabling and disabling the KSM daemon. So for this test, we first launch the hello world unikernel in background with an infinite loop, and then so we run the SQLite unikernel. And yes, for this one, so we generated 12 tables. We did more than 15,000 insertions. And finally, so we did more also that 100 selects with complex queries. And we can do two different observations. So the first one is that we have a considerable overhead when KSM is enabled. So indeed, since KVM is scanning and is looking for pages to merge in real time, so it will consume some CPU cycle, and this it will have a considerable impact on the task performance that it is working on. And the second observation that we can do is that aligned unikernels have also a better performance. And so yes, we can see that we gain some performance since the completion time of aligned unikernel is a bit faster. But yeah, for this part we need to do a further investigation, but we think that it is related to the cache locality principle. So as a conclusion, so we can say that having several unikernels instances which have different microlies configuration has a considerable impact on the memory sharing. Fortunately, so it is possible to circumvent this issue by aligning microlips and section in the same memory location via a kind of map. And this map will allow to decrease the memory usage and will considerably increase the overall performance of the underlying system. So, and the general idea of our work is to inflate unikernels in order to make them smaller. And basically, yes, I think that I'm more or less in time. So thanks a lot for your attention. So I hope that it was a bit interesting, and feel free to ask all the questions. Thanks a lot. Razvan, don't know if...
I wanted to ask something. Missing order of the microlibs is not going to affect dependencies or something?
The order question.
Yeah. So you mean if we use different microlibs? So I don't get it exactly. Yeah.
I was basically thinking about the fact that when we use that makefile.uk, we had to put external libs in an order because of dependencies, I guess. And if you're going to mess the different libraries in order to get them aligned, is this not going to affect the running of Unikernel?
No, because when we it depends on the map, and for the map, so we have aligned all microlibs and the respective dependency at specific addresses. So basically, our algorithm will also handle this case.
I have a question.
Yeah, sure.
What about the computational complexity of aligning the different microkernels? And, like finding the perfect alignment, that sounds like an NP-hard problem.
Yeah, so basically to find the perfect alignment, so it is quite complex, so it is quite complicated because we can have several permutations, so and it is quite difficult, but basically we have tried to built a unikernel with a maximum of microlibs, and we computed the map of all these microlibs. But if we want in the future to insert new microlib, we need to recompute this map. So at each time we will add a new microlibs, we need to recompute this map. Yeah. But basically, so we need to do some investigation in order to see if there is another possibility, but for now, yes, we are still in a research phase.
Yeah, like 2 years ago, I started developing a small operating system with a friend of mine because we didn't like the OS lecture that we had to listen through. And we kind of came up with a similar concept of placing libraries at page boundaries and mapping them into each other's memory to avoid dynamic linking.
Yeah, I see.
And improve application startup times. But we had a similar issue. Well, we thought we would have a similar issue with computational complexity. And is it possible to, at runtime, rewrite the library to, first of all, like run a program and have it rely on some relocation math? So it looks up. So you basically have a shim, you have a proxy for the different library calls. And then you do relocation, and at runtime you can replace it. That's something that could theoretically be possible. And another issue we had was with like different versions of libraries, and what happens if the location of the binary location of different functions changes over time.
I see. Yes, for this part, yes, we need to do a further investigation, but I think that it will be possible. So we just need to think to something a bit smarter. But yes, it will be some future work about our research.
But yeah, this is really fascinating, and I would love to stay up to date with it.
Yeah, sure. Thanks.
I think that it's a very good idea to follow us, and I mean, if you're part of this channel, is for sure when there's any sort of updates from Gaulthier publications or everything, you're bound to find that out. I mean, we're likely going to announce it on Twitter. Gaulthier has been working on this for some time, and it's for sure going to provide some very interesting results.
Yeah.
Yeah, I'd love to play around with it.
Thanks a lot.
Awesome. All right, any other questions? Okay, Gaulthier, thank you so much for the this engaging talk. We hope to get more results, and I think the interest of the audience is obvious. Thank you so much. I'm going to ask you when you have time to, whatever means of communication, if you can provide us the slides to link them somewhere. And everyone, we're going to, so this was made live. It's now part of YouTube. We're going to also announce the link on the USoC'21 playlist for the Unikraft channel. That being said, Gaulthier, thank you so much for your time and for your talk, and we keep in touch.
Yeah, thanks. Bye bye.
Everyone, we meet on the main channel, the USoC channel, in 1 minute to continue